Rotondo in Italy. And today I will present to you a work carried out by me and my supervisor, Pietro De Ellis, concerning the pinning control in networks of nearly identical systems in the presence of high-order interactions. Just a moment. Okay. Okay. Network science has attracted a relevant research effort in the last decades. In particular, the emergent dynamics exhibited by complex systems is describing a plethora of natural collective phenomena, is the result of the interplay between the dynamical units composing complex systems. The applications related to this topic are extremely numerous. Just think about the opinions or epidemics diffusions, or the functioning of power smart grids. Today, scientific literature is rich of works concerning complex systems where the interactions between their dynamical units can be easily decomposed as a combination of pairwise ones. Historically, these kind of interactions have been generally modeled through digraphs. So consequently, the control signals we need to control complex systems have been schematized as directed edges that connect the virtual controller node, that is also called the pinner, to the rest of the network. However, there exist several real-world applications in which the multi-body interactions between the dynamical units of complex systems cannot be factorized in pairwise ones. Just let's give a look to this simple example related to opinion dynamics. So in this case, the presence of the two pairwise interactions means that the opinion leader is able to individually measure the opinions of the two followers and send two depersonalized signals to them according to their opinion. In this case, we have nothing different from the ordinary because this kind of scenario can be easily modeled through a controlled complex systems coupled through a directed graph. And we know that the dynamics associated to the ith individual will be affected by this very known and studied communication protocol. Now, if we replace the two pairwise interactions with a unique multi-body one, we are assuming that the opinion leader can only measure an aggregated opinion of the two followers and send to both of them only the same signal based on such aggregated opinion. So in this case, we need to model this other kind of scenario. We need to introduce a new tool from discrete mathematics called directed hypergraphs, and we need also to implement a different communication protocol. Well, the presence of high-order interactions can cause unexpected dynamical behavior. In fact, once the dynamics associated to the three agents of the previous example have been simulated according to these two sets of equations here, we noted that when the opinion leader is able to individually measure the opinions of followers, the corresponding complex systems exhibit consensus. On the other hand, when in the presence of sensing constraints, so when the opinion leader can only measure an aggregated one related to the two followers, the corresponding complex system does not exhibit the same collective behavior. So, throughout our research, we questioned which are the mechanisms that can somehow induce the collective behaviors in complex systems, especially when their interacting topologies are described by hypergraphs, and how can we select the pinning control strategy that can favor somehow the onset of such collective behaviors. So before going on, I need to formally define what is a directed hypergraph. A directed hypergraph is defined as a pair of sets. The first of them is the set of nodes, set V, while the second one is the set of the hyperedge. An hyperedge is in turn defined as a pair of ordered and disjoint subsets of V. The first of them will contain the hyperedge tails, while the second one will contain its heads. From the dynamical point of view, we have that each tail will send a signal to each head, and this signal will be a function of the output of all the nodes that are joined at the same time by the same hyperedge. So let me now describe the model we have used in our work, affecting the dynamics of the ith node. It is composed by different terms. The first of them encodes the effect of the individual dynamics associated to the ith node. Now we know that in several applications, interacting units cannot be identical. In fact, for instance, in opinion dynamics framework, we have that people cannot be modeled with identical individual dynamics because they may be characterized by different levels of stubbornness or extremism, let's say. So our model takes into account the presence of such kind of heterogeneity between the between the interacting agents, because the individual dynamics is affected by a parameters vector, which can vary from node to node. The second term is the coupling one, which takes into account the presence of multi-body interactions. And as you can see, the general term in the summation is related to the average epsilon. In particular, it contains its coupling strength sigma and the inner coupling function g, whose input is given by the difference between convex combinations of tails and heads outputs respectively. Such outputs are defined by the output function gamma, and finally, we can introduce the pinner dynamics, whose trajectory will be the reference one for the whole network, and the control term UI, which is related to all the averages that communicate the reference trajectory to a small fraction of nodes. Now, upon the introduction of heterogeneity in our model, we noted that the only collective behavior we can achieve is bounded synchronization. So we defined the convergence bound C as a quantity such that this condition here holds. And then our research question became, how can we guarantee somehow a bounded control error? Or how can we select the pinning control strategy that is able to minimize such collective behavior? Such convergence bound C. So, to give an answer in this work, we provided sufficient conditions for the achievement of local bounded and pinning control synchronization. We provided mathematically backed estimation of such convergence bound C, and we used such estimation to identify the control strategy that can better cope with the given parametric mismatch. So, in the next slides, I will briefly outline the key steps we took in order to achieve our main result. So let's, first of all, we started from the model that I have already shown to you. And then we consider the dynamics of the ith error variable that is defined as the difference between the ith node trajectory and the pinner one. Then we linearized such dynamics around the pinner trajectory and parameters. And then we put together all these linearized dynamics in order to obtain a unique linear and time-varying system describing the error dynamics of the whole network. Matrix M, you can see in the dynamical equation, accounts for the effect of the interacting topology and of the control averages. After that, we applied the real transformation matrix TR in order to turn matrix M in matrix JR, where matrix JR is the real Jordan canonical form. Thanks to this transformation, we obtained a partial decoupling between the eigenmodes associated to the system. In particular, the eigenmodes associated to the ith Jordan block will not depend on the eigenmodes associated to another one. As you can easily note from this set of equations, after the transformation, the dynamics associated to the ith Jordan block are still coupled together. But thanks also, by giving a look to this picture, we can note that the dynamics of the eigenmodes eta ij depends on the dynamics of the eigenmode eta ij-1. And this is the reason why we have studied the convergence of such dynamical systems in a very convenient algorithmical manner. So we are now ready to state our main result. So let me describe the assumptions of our theorem. They are related to three matrices. The first of them is matrix AI, which depends on the individual dynamics F and on the ith eigenvalue of matrix M. Then we have a matrix QI, which is constant and positive definite, and it appears in the Lyapunov equation you can see on the screen, whose solution is the time-varying matrix PI, that will be very important in the next slides. And then we have matrix BI, which takes into account the effect of parameter mismatches. Now, if all the assumptions you can read on the left are fulfilled, we have that the network reaches local bounded synchronization, and the error norm will be less equal than the estimated convergence bound C tilde that is defined, as you can see on the bottom. In particular, the element Ci is the estimated bound of the norm of eta I, where eta I is a vector containing all the eigenmodes associated to the ith Jordan block. For the proof of the theorem, we have applied the Lyapunov stability theory, and we have chosen the quadratic function you can read as the Lyapunov function, whose kernel is given by the time-varying solution of the Lyapunov equation of the previous slides. Now, I can show to you some numerical result. So as a first test, we evaluated the robustness of our estimation methodology. So we considered an hypergraph, an Erdos-Cherveny-like hypergraph composed by 100 Rossler systems and with pairwise and triadic interactions. The parameters of each Rossler system have been drawn from a uniform distribution centered into the Pinner parameters, and whose amplitude is given by the product between the Pinner parameters and the hyperparameter psi. As you can see in the picture, we plotted the ratio between the estimated and the actual bounds, and we versus the parameter psi. And as you can note, our estimation methodology is very, very effective, also in case of very large parametric mismatches, both in case of 20 and 50 control hyperedges. Finally, we used our estimation methodology to effectively control the opinion dynamics. Just a moment. Don't know what. No, I don't know. Just a moment. Sorry. Strange. Okay. We used our estimation methodology to effectively control opinion dynamics to favor, for instance, the diffusion of safety social norms between interacting people. So, sorry. Just a moment. Okay. So, we considered an opinion leader that wants to steer the followers' opinion toward its own, and that such followers are divided into 15 communities, and that the opinion leader can directly influence only one of them because of the presence of actuation constraints. So thanks to our methodology, we were able to select the community that should be pinned in order to minimize the disagreement between opinion leader and followers. To do that, we considered a real-world hypergraph composed by 150 interacting people that need to form an opinion on a two-option choice. So consequently, we set the individual dynamics as you can see on the screen. In particular, this model has 3 equilibria. The first of them is the origin, that is unstable, and the other 2 are symmetric and stable. They are associated to the 2 options people can choose from. Now, as you can see from this animation, they are farther from the origin the larger the parameter mu I is. In fact, the parameter mu I is associated to the extremism level of each individual. In this framework, our control goal is to minimize the convergence bound C by pinning only one community among the 15. To do that, we computed the estimated and the actual bounds when each community is pinned in turn. And then we selected the community associated to the lowest convergence bound. So we selected community number 4 because it is associated to the lowest convergence bound, estimated convergence bound. Then we computed the correlation between estimated and convergence and the actual convergence bound that is very high, as you can see from this data. And since the community rankings obtained by both sets of bounds are basically identical, our previous choice turned out to be the optimal one, also according to the actual convergence bound. So to summarize, in this work, we provided sufficient conditions for the achievement of local bounded and pinning control synchronization in the presence of high-order interactions. We estimated the convergence bound by studying the linearized dynamics and without the need for simulating the network. And finally, we numerically showed that there exists a very strong correlation between the estimated and the actual convergence bound, that our estimation methodology is very, very effective also in case of very large parametric mismatches that would make the individual dynamics unstable if uncoupled. And finally, that it can be effectively used to identify the most suitable pinning control strategy according our control goals. So this concludes my presentation. So please scan this QR code if you are interested in our work. Thank you for your attention.
Thank you.
I'm sorry for the length. Sorry for the length.
Is there a quick question? Some quick question for Roberto? Well, if there are no questions, let's thank Roberto again. And Let's clap. And we go.